Section 8.2, Polar Graphs. So, we're going to work on the polar grid. We're going to do exactly what we did previously, but please recall that from that last section, we have these things called polar coordinates, which are of the form r theta. And the ideal way to plot polar coordinates is on a polar grid. And so let's remind ourselves how to do that. If we are given these ordered pairs, r theta, where we have 5 pi fourths, recognize that if I'm going to work on this thing, well, I'm going to label some of these. How about 1, 2, 3, 4, 5, and then I can label this pi fourths, pi halves, 3 pi fourths, pi, 5 pi fourths, 3 pi halves, 7 pi fourths, and then of course this is 0 and 2 pi over here, but I'm not going to label that one for the sake of space. Alright, so 5 pi fourths, go out to 5, rotate pi fourths. Here's my point A. Then let's convert that to rectangular coordinates. Remember that rectangular coordinates we can get for free as x is equal to r cosine of theta and y is equal to r sine of theta. And so my rectangular coordinates are then going to be 5 cosine of pi fourths, and my y-coordinate is 5 sine of pi fourths. And then of course this becomes 5 root 2 over 2, 5 root 2 over 2. And for the sake of approximation, how about 5 root 2 divided by 2 is approximately 3.54. And so then if I go to 3.54, and then I go up 1 to 3.54, that's exactly where I expect it to be, or at least pretty close, and so we're safe there. Then I need to graph negative 2, 5 pi 6, and 5 pi 6 is going to occur about, actually right here. So then what we can do is we can go out to negative 2, and then rotate 5 pi 6 in the positive orientation, which puts me right here. Okay. Then I need to check the rectangular coordinates, so let's convert to rectangular. And the rectangular coordinates are then negative 2 cosine of 5 pi 6, negative 2 sine of 5 pi 6. Well, then that's going to be negative 2 times negative root 3 over 2, and negative 2 times positive 1/2. That gives me square root of 3, negative 1. And so let's confirm that that's right. So real quick, root 3 is approximately 1.73. And so root 3 negative 1 is 1.73. It's in here somewhere. And then go down 1. Look at there, it lines up exactly where we expected. So great. An equation whose variables are polar coordinates is called a polar equation. And the graph of a polar equation consists of all points whose polar coordinates satisfy that equation. And so we learned last week that we can convert these to rectangular coordinates if we so desire. And so that's actually how we're going to start this. First, we want to identify and graph the equation r equals 3, but before we do, we're going to do all that by converting it to a rectangular equation. And so remember that r is equal to the square root of x squared plus y squared. And so then converting to rectangular, I get square root of x squared plus y squared is equal to 3. And then square both sides, we get that x squared plus y squared is equal to 3 squared. Well, now I can identify this, because this is specifically a circle centered at 0 with a radius of 3. And so I go out to a radius of 3 centered around 0. And if I could stay on the line, that would be x squared plus y squared is equal to 3 squared. But notice also that that's the place where the radius is equal to 3 for the polar equation, and so the polar equation comes out a little quicker. It's nice, easy, we're done. Now we want to do the exact same thing here. We have r sine theta is equal to 2, but recall that y is equal to r sine theta, and so that is y is equal to 2. And if y is equal to 2, what does that graph look like? Well, y being equal to 2, there it is right there. That's y is equal to 2. And this is a horizontal line. Alright. Let's try r cosine theta is equal to negative 2. Well, of course, x is equal to r cosine of theta. And so that means that x is equal to negative 2. X being equal to negative 2 looks like this. This is going to be a vertical line. Alright, so now let's identify and graph the equation. Theta is equal to pi thirds. Well, recall that tangent of theta is equal to y divided by x. And so that means that theta is equal to tan inverse of y over x, which then means that tan inverse of y divided by x being equal to pi thirds, take tangent of both sides, that means y divided by x is equal to tangent of pi thirds. So then I get y is equal to root 3. Y divided by x is equal to root 3. Then I can multiply both sides by x, and I get y is equal to root 3 times x. And so now I know that my slope is root 3. And so I have the y-intercept of 0. Now specifically, if you notice, if we go back to the original equation, theta being equal to pi thirds, you're just looking for everywhere that theta is equal to pi thirds. I think that's actually ending up being a little bit easier to find on this specific grid versus that slope of root 3. But recall that root 3 is approximately 1.73 to check yourself, which means that rise over run, we go up 1.73, and then we go right 1, and look at there, we actually end up right there. And so if I connect the dots, notice that that is my line segment. Y is equal to root 3 times x, but it's kind of nice on this grid because it's the situation where theta was equal to pi thirds for all positive and negative and 0 r values. And so this is just a line. Now we want to write the following equation of a circle that's given in general form in standard form, but to put it in standard form we need to complete the square. And recall that standard form is x minus h quantity squared plus y minus k quantity squared is equal to r squared. And so that's the standard form of a circle, and so let's get it in that format. I'm going to go ahead and rearrange all this and leave some spaces. And so I have x squared minus 3x plus a space plus y squared plus 2y plus a space. I'm going to go ahead and move that 3/4 over so it's equal to 3/4 on the other side. Well, really you're completing the square for two pieces, so remember that your magic number to add is b over 2 quantity squared. And so here, if I have plus negative 3 over 2 quantity squared, I add it over here, plus negative 3 over 2 quantity squared. And then here I add the same thing, positive 2 over 2 quantity squared, add positive 2 over 2 quantity squared. Then, if you recall, completing the square at this point is really quick and easy because it's just going to be x and then write whatever this number is with a matching sign, and so that's going to be in parentheses. So this is x minus 3/2 quantity squared plus y plus 1 quantity squared is equal to, and on the other side we're just going to simplify that, 3/4 plus 9/4 plus 1. And so simplify further, that's x minus 3/2 quantity squared plus y plus 1 quantity squared is equal to 9, 10, 11, 12, 12/4 plus 1. 12/4 ends up being 3, 3 plus 1 is 4, and so this is x minus 3/2 squared plus y plus 1 quantity squared is equal to 4. Now, it might be useful to also rewrite that as 2 squared, because then we know that this equation that I have here is a circle centered at 3, 2, negative 1, with radius 2. We did all that because maybe we're going to need it in a moment. R equals 3 sine theta. Step 1, convert this to rectangular coordinates. So let's multiply both sides by r. Then I get that r squared is equal to 3r sine theta. Then r squared is equal to x squared plus y squared. R sine theta is equal to y. So then we need to get everything to one side. Let's subtract 3y from both sides. When I do this, I'm going to go ahead and reorganize it. X squared plus y squared minus 3y plus, leave some space, is equal to 0. Then we need to add b over 2 squared. So that's going to be negative 3 over 2 squared to both sides. Then this factors nicely as x squared plus y minus 3 over 2 quantity squared, which is then equal to 9/4. Or of course 9/4 could be written as 3/2 squared. Then we note that we have a circle with center, remember to change your signs, being 0, 3/2, and the radius is equal to 3/2. So our center, go up to 3/2, and then I'm going to go up 3/2 for my radius, down 3/2, left 3/2, and right 3/2. Then notice that if I could draw this circle correctly, it is tangent to the pole, and r equals 3 sine theta shifted it up vertically, and so circles of the form r equals something times sine theta will shift them vertically up or down. So if I've got r equals 2 cosine theta, do the same thing, multiply both sides by r. I then get that r squared is equal to 2r cosine theta. That's then going to give me r cosine theta is x, r squared is x squared plus y squared is equal to 2x. Subtract 2x, subtract 2x. That's then going to be x squared minus 2x. Leave a space. Plus y squared is equal to 0. Add that magic number, that is b over 2 quantity squared. So add that to both sides. Then this factors as x minus 1 quantity squared plus y squared is equal to 1 squared. Then I get a circle centered at 1, 0 with radius 1. And so 1, 0, just as a whole placeholder, has a radius of 1. So here, 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 and here. If I had a compass, I'd have a much better circle. Notice now that I can say that r is equal to something times cosine of theta means it's probably going to be a circle shifted left or right. Now, polar equations, just like rectangular equations, can have symmetry. And so let's talk about the symmetry based on these pictures. Notice that if I look at this one on the left-hand side, be careful because this arrow here is just my polar axis. And so when I'm looking at this one is actually symmetric with respect to the x-axis. And so this one has x-axis symmetry. And for the record, remember I just said that this also has, this is the polar axis here, and so this is x-axis symmetric, which also is polar axis symmetric. Okay? Now this next one, if we look at this, well, this one is y-axis symmetric, right? And so y-axis symmetric. And so what we're going to refer to this one as is this one's going to have symmetry to theta is equal to pi halves. And so symmetry with respect to theta is equal to pi halves, because that's really describing the y-axis. Then I get to this other one. Notice, what does this one have? Well, if you rotated 180 degrees, or you turned upside down on your head and you looked at it upside down, this one would have origin symmetry. And so origin symmetry for us is going to be symmetry with respect to the pole. Now recall that the pole is the origin, right? Now we have some tests that given a polar equation we can test for specific symmetries. Now I have a little bit of a caveat we'll have to discuss later, but understand that this just tells us if those symmetries do occur. So if we want to test if this function has a symmetry with respect to the polar axis, that is the x-axis, in a polar equation what we're going to do is we're going to replace theta with negative theta. And then if we simplify that statement as much as we can and we get an equivalent equation, then we're going to say that the graph is symmetric with respect to the polar axis. Well then, if we want to test symmetry with respect to the line theta equals pi halves, that's y-axis symmetry, then in a polar equation we're going to replace theta with pi minus theta. If an equivalent equation results, then the graph is symmetric with respect to the line theta equals pi halves. And then to test symmetry with respect to the pole, or that is the origin symmetry, in a polar equation we're going to replace r with negative r, or replace theta with theta plus pi. If we get an equivalent equation, the graph is then symmetric with respect to the pole. Now that caveat I said is that these tests are what we call sufficient conditions for symmetry, but not necessary conditions. What that specifically means is that if the test fails, that doesn't mean that symmetry doesn't exist. And so you have to be a little bit careful. The only thing that these tests do is that if you do the test and you find the result to be true, then you have shown that yes, those symmetries exist. But the other direction is not true. Okay, just because the test failed doesn't mean it kicks out those symmetries. Alright, so now we're going to try to graph polar equations. Now the big reason that I say use symmetry is because what we're going to do is we're going to test for symmetries, and when we test for symmetries, we might be able to cut down the points that we plug into these polar equations when we graph them to make our lives a little bit easier, because if we have symmetry we might be able to deal with half the points plugged in. So r is equal to 2 plus 2 cosine theta, and we want to test for the symmetries. Let's start with polar axis symmetry. So to test polar axis symmetry, what we need to do is we replace theta with negative theta. Alright, let's try it. So we get r is equal to 2 plus 2 cosine of negative theta. We then have that r is equal to 2 plus, well, cosine is an even function, recall. Therefore, cosine of negative theta is exactly the same thing as cosine of positive theta, and therefore we can say yes, we have polar axis symmetry. Alright, but we should test the other things just to see if we get multiple symmetries, because if by chance you got multiple symmetries, maybe you could save time. So let's test for symmetric to the line theta is equal to pi halves. What are we going to do with this one? We're going to do theta, replace theta with pi minus theta. So then I get that r is equal to 2 plus 2 cosine pi minus theta. But then I want to use a difference identity, so that's going to be r is equal to 2 plus 2 cosine of pi. Got to be a little bit careful here. I need to put a bracket there. Cosine pi cosine theta minus, in the cosine sum identity, minus gives plus. So plus sine pi sine theta. And so then let's see if this simplifies. R is then equal to 2 plus 2 times cosine of pi is negative 1. So that's negative cosine of theta. Plus sine of pi is 0, so 0 times sine of theta is 0. And so notice that we get r is equal to 2 minus 2 cosine theta. And test failed, and so all we can say is that the test failed, which means that it's inconclusive. We can't say that it's not symmetric to that axis, we just don't know. That's what I was trying to say earlier. So now let's do the last symmetric test. So symmetry with respect to the pole. Remember that one we're going to replace r with negative r, or theta with theta plus pi. And so for this one, I think theta plus pi with theta is going to be a little easier, because then we can use our identity. And so that's going to be r is equal to 2 plus 2 cosine of theta plus pi, then cosine identity, and so we get r is equal to 2 plus 2 times cosine theta cosine pi plus gives negative sine of theta sine of pi, and so then that's going to be r is equal to 2 plus 2. Cosine of pi is negative 1, so that's negative cosine of theta. Sine of pi is again 0, so that's minus 0, but once again we now have r is equal to 2 minus 2 cosine theta, and so this test failed, but that doesn't tell us that that symmetry doesn't exist, it just says that we can't guarantee that it does. Okay, but we do have polar axis symmetry. If we have polar axis symmetry, we have symmetry with respect to the x-axis, which means above and below are the same, which makes me think that if I'm going to pick a value for theta to plug in, all the thetas that I need to plug in are really the stuff that's the top half of the x-axis, or I'm going to pick these values between 0 and pi. Because if I pick those values, then once I start getting past pi and cycle back around, I know they're going to have to repeat because of my symmetry. So let's plug these in. So if I plug 0 into my equation, 0 in for theta, that's going to give me r is equal to 2 plus 2 cosine of 0. But cosine of 0 is 1, and so we're then going to get 4, 0. Alright, I'm just going to plot these ordered pairs as I find them. So 4, 0, right there. Then plug in pi 6, so I get 2 plus 2 cosine of pi 6, which then I'm going to go ahead and approximate to make my life easier on plotting, and I get that's about 3.73 pi 6th, and so let's cycle to pi 6th, and 3.73 pi 6 is about right there. Then let's do pi fourths, so plug in pi fourths, that gives me approximately 3.41 pi fourths, so 3.41 pi fourths, 1, 2, 3.41, that's about right there. Then pi thirds, that's going to give me 3 on pi thirds. Now, if we want, we could go ahead and mirror these points down here because we know that we're going to have symmetry with respect to the x-axis. And so why don't we go ahead and do that. We have this ordered pair, then we have this one, then we have this one. Alright, so then let's do pi halves, plug in pi halves. Sorry, we have theta, we should have pi halves. Well then what do we get? We're going to get 2 pi halves, and so 2 pi halves, and of course we get the mirror point, 2 pi halves, well really negative 2 pi halves. Then 2 pi thirds, plug that in, what are we going to get? We're going to get 1 2 pi thirds. 1 2 pi thirds is about right there, and then our mirror point. Then plug in 3 pi fourths. 3 pi fourths, when we plug it in, we're going to get 0.59, about right there. Then 5 pi sixths, we get about 0.27, and so that's going to be about right here, mirror point about right here. And then if I plug in pi, we're going to get 0, and so I get that. Now, I'll go ahead and sketch this for you, but it looks something like and so specifically this is going to be what we call a cardioid. So this is a cardioid. Alright, let's graph another one. Here we have 4 minus 2 cosine theta. Let's check this one for symmetry. So now let's test this one for symmetry. So let's first test with respect to the polar axis. And so we replace theta with negative theta. R is equal to 4 minus 2 cosine of negative theta. This one Remember that cosine is even, so we get r is equal to 4 minus 2 cosine theta. And so we get that, yes, we have polar axis symmetry. So then let's test for symmetric to the y-axis, or to theta is equal to pi halves. Remember, for this one we're going to replace theta with pi minus theta. Now the truth is because this is cosine, recognize that this isn't going to work, and so this one's going to fail just like the last one did. But that doesn't tell us that it doesn't have that symmetry. We just don't know if it does. And then let's do symmetric to the pole. And so symmetric to the pole is going to be theta plus pi. Symmetric to the pole is one of two tests. It's either r with negative r, but if you do r with negative r, we didn't do that one last time, we get negative r is equal to 4 minus 2 cosine theta, but if you divide by negative 1 on both sides, you cannot get the exact same equation, so it's going to fail again. And so the test fails. And so then we get that r is equal to negative 4 plus 2 cosine theta, but that means that the test fails. Now, we do know that at this point we can say, oh, well, we do have polar axis symmetry, which means that having polar axis symmetry we can just deal with between 0 and pi because that's the top half of our circle, and so we're going to do that again. So, doing the exact same thing, remembering that we have that polar axis symmetry, I'm going to plug in 0 here. What do we get? We're then going to get 2, 0. So 2, 0. Then plug in pi 6, 4 minus 2 cosine pi 6. If I approximate that, I claim we get 2.27 pi 6. And so 2.27 rotational of pi 6 is about right here. But if we want, we can go ahead and start working on those mirror points. So 2.27 pi 6, it's about right there. Then let's try pi fourths. So that gives me 2.59. And so 2.59 is going to be about right there. And then of course the mirror point. Then try pi thirds. 4 minus 2 cosine pi thirds. That's going to give me 3 pi thirds. So 3 pi thirds, but I get the mirror point down here. Then pi halves. 4 minus 2 cosine of pi halves. That's going to give me 4 pi halves. So 4 pi halves, mirror point. Then 4 minus 2 cosine 2 pi thirds, that's going to be 5 2 pi thirds. And then we get the mirror point. Then 3 pi fourths, that's going to give me 5.41. 5.41 is about right there. And then we of course get the mirror point. And then for 5 pi 6, I get 5.73. So let's go a little further. And then the mirror point. And then for pi, I get 6. And so that's about right here. And so this one looks about, it's almost flat on the far right, but not quite. And so here's the graph. Now this graph is pretty close to the cardioid, but it's not quite the same. And the deal is that this is actually what we're going to call a limaçon, is a French word for snail. And so essentially the idea is that this looks like a snail shell, and that's the reason that that was given this name. Okay, let's do this one. So let's test our symmetries. So first, let's check with symmetry with respect to the polar axis. So polar axis symmetry, we're going to replace theta with negative theta. So r is equal to 1 plus 2 sine negative theta. But sine is an odd function, so test fails. And we don't actually know if it has polar axis symmetry. Then we test symmetry with respect to the y-axis, or theta is equal to pi halves. That one we do by taking and replacing theta with pi minus theta. And so then we get r is equal to 1 plus 2 sine pi minus theta. Here we use our difference identity. So r is equal to 1 plus 2, put a bracket. Sine pi minus theta is going to be sine pi, sine theta, sine pi, cosine theta, minus cosine pi, sine theta. But then this gives us r is equal to 1 plus 2. Sine of pi is 0, times cosine theta is 0, minus cosine of pi is negative 1, times sine of theta. And so then we get that r is equal to 1 plus 2 times positive 1 sine theta. This checks out. That means we have, yes, symmetry with respect to theta is equal to pi halves. And so we do have that symmetry. And for the sake of it, we can check the pole real quick, but we can do this one really easily because pole symmetry can be checked really easily by replacing r with negative r, but then negative r is equal to 1 plus 2 sine of theta. Divide by negative 1, we get that r is equal to negative 1 minus 2 sine theta. And so that is not the same equation. There's not really a way to manipulate it. So this test fails. Alright. So since we have symmetric with respect to the y-axis, or with respect to pi halves, we're going to specifically pick theta values that run between negative pi halves and pi halves. And so that's what I've got laid out here. So we plug in negative pi halves, and we're going to get negative 1, but be careful, because that means that when I come down to negative pi halves, then this is really the point, right? Go to the radius of negative 1 and rotate negative pi halves. Then for symmetry being across the theta is equal to pi halves, that is on itself as a mirror point. And then plot the point that we get for plugging in negative pi thirds. I get negative 0.73 at negative pi thirds, so negative 0.73, and then rotate clockwise pi thirds. That's about right there, which gives me a mirror point over here. Then plug in negative pi 6, I get 0 negative pi 6, so 0 radius. Then plug in 0, and at 0 I get 1 0, so 1 0, and I get a mirror point. Then let's plug in pi 6. When we plug in pi 6, we're going to get 2, so go to 2 pi 6. This is a little strange, but then I of course get the mirror point, 2 pi 6 over here. Then I plug in pi thirds, and I get 2.73 at pi thirds, so 2.73 at pi thirds. That's going to be about right there. And I of course get its mirror point. And then plug in pi halves, and I'm going to get 3 pi halves. And so I don't get a mirror point. Now this is a little odd, and you may be confused as to what in the world this looks like. Now I'll summarize all this at the end, but I'll show you what this sketch should be. This sketch should be something like this. And this is actually a limousin with an inner loop. Let's do another. Here we have r is equal to 3 cosine of 2 theta. We want to figure out if this thing has any symmetry. Let's test r is equal to 3 cosine 2 theta for symmetry. So let's start with symmetric to the polar axis. So we're going to replace theta with negative theta. That's then r is equal to 3 cosine of 2 times negative theta. But we know that cosine is an even function, so this is then r is equal to 3 cosine. The negative pulls out, and we're just left with 3 cosine 2 theta. And so this one, yes, is symmetric with respect to the polar axis. Then let's test and see if it has symmetric to the y-axis, or symmetric to theta is equal to pi halves. So we're going to take and replace theta with pi minus theta. And so that's going to be r is equal to 3 cosine 2 times pi minus theta. So that is r is equal to 3 cosine 2 pi minus 2 theta. Then I can use my difference identity. R is equal to 3 times cosine of 2 pi cosine of 2 theta minus plus sine of 2 pi sine of 2 theta. Well, recall that this is now going to be r is equal to 3. Well, cosine of 2 pi is just going to be 1, and so that's going to be cosine of 2 theta, plus sine of 2 pi, but sine of 2 pi is going to be 0, and 0 times 2 pi is 0. And so we do get the exact same thing we started with. We get that r is equal to 3 cosine 2 theta. Alright, so that means that not only is it symmetric with respect to the polar axis, yes, it's symmetric with respect to the y-axis, or to theta is equal to pi halves. And so we have two symmetries here for certain. Let's test for the third. And so symmetric. So let's test the symmetric with respect to the pole. And so this time I'm going to replace it with, I'm going to replace theta with pi plus theta. And so theta with pi plus theta. That's then going to give me r is equal to, I'm going to cut this off real quick so I don't run into it. R is equal to 3 cosine of 2 times pi plus theta. Well, that's going to give me r is equal to 3 cosine of 2 pi plus 2 theta. Well, then that's going to give me r is equal to 3 times cosine of 2 pi times cosine of 2 theta minus sine of 2 pi sine of 2 theta. But then this is r is equal to 3 times cosine of 2 pi is 1, so that's times cosine of 2 theta, minus sine of 2 pi, but sine of 2 pi is 0. 0 times sine of 2 pi is 0, and so we get that this is r is equal to cosine of 2 theta. So specifically, this also has origin symmetry, or symmetric with respect to the pole. And so what's going to happen now is that when I plot these points, I'll only have to pick points from the first quadrant. And then I know that they'll mirror across the y-axis, they'll mirror across the x-axis, and they'll mirror with a 180-degree rotation onto the other side. And so let's see what happens. So I'm going to pick some points, some nice points from the first quadrant. So let's plug in 0. If I plug in 0, pretend I didn't write theta there, but instead I wrote 0. Then I'm going to get 3, 0. Okay, so 3, 0, I get. Alright, well that's the symmetric with respect to the x-axis, but then symmetric with respect to the y-axis is going to put me over here. That's also going to give me, that's exactly the same as symmetric with respect to the pole as well. Alright, so then let's try pi sixth, and if I plug in pi sixth, then I'm going to get 1.5 pi sixth is right here, but it is going to mirror, so I get it also right here. It's also going to mirror across the y-axis, so I also get it right here. And then it goes around the origin, so it also mirrors right here. Okay, so I get all those points. Then let's plug in pi-fourths. If I plug in pi-fourths, I'm going to get 0 pi-fourths. And so I get that point, but that's all my mirror points as well. Then for pi-thirds, plug it in. What am I going to get? I'm going to get negative 1.5 pi-thirds. So let's see what that happens. So if I go negative 1.5, and then I rotate pi-thirds, we're here. Then mirror across the y-axis, right here. Mirror across the x-axis, right here. Rotate around the origin 180 degrees, I get right here. Okay. Then let's plug in pi-halves. If I plug in pi-halves, I'm going to get negative 3 pi-halves. So negative 3, and then pi-halves rotation is this point, and then I get the mirror point over here. Now let's sketch what we get. I claim this will look like, and I may not be drawing it in the correct order. But here we have a rose with 4 petals. Now I do have to distinguish, because not only will we get roses with 4 petals, we may see roses with 3 petals. Okay, so now we have r squared is equal to 9 cosine of 2 theta. Let's see what we get with this one with regards to symmetry. So step 1, we're going to deal with symmetry with respect to the polar axis. And so that is theta with negative theta. So that is r squared is equal to 9 cosine of 2 times negative theta. Well, cosine is an even function, so r squared is equal to 9 cosine of positive 2 theta. So, yes, polar axis symmetric. Then let's see if we have y-axis symmetry or symmetric with respect to theta is equal to pi-halves. That one's going to be replace theta with pi minus theta. And so that is r squared is equal to 9 cosine of 2 pi minus theta. And I claim that this one, just like earlier, is going to give us cosine of 2 theta in the end using the sum identity. So I'm going to skip it for now. And we get that r squared is equal to 9 cosine of 2 theta. And yes, that works. Once again, that's because of the difference identity. Then, if we want to know symmetric with respect to the pole, or the origin, that's going to be to replace theta with theta plus pi. And so that's going to be r squared is equal to, now notice that we could use theta with theta plus pi, or we could use r with negative r, and I'm going to choose that one because then I don't have to use the identity and I can get there just as quick. So if I replace r with negative r, that's negative r squared is equal to 9 cosine of 2 theta. And so once again, we get r squared is equal to 9 cosine 2 theta. And so yes, this one also has symmetry with respect to the pole again. So once again, we can play just in the first quadrant. Now specifically with this r squared is equal to 9 cosine 2 theta, that means I'm just going to have to take the square root of the right side to get r once I plug in theta. And so cosine of 0 is going to give me 1 times 9. Square rooted is plus and minus 3 because of the square root, right? We take the square root of both sides as plus and minus 3. So when my rotation angle is 0, I'm going to get positive 3. I'm also going to get negative 3. Okay? Then when I plug in pi 6, take the square root of both sides, you get the plus and the minus. This is going to give me plus or minus 2.12, and we have all of the symmetry. So pi 6 plus 2.12, so that's about right here. I also get, maybe I'll do the plus first and I'll deal with the symmetry. So there's that one. Then via symmetry, I get this one, and then origin symmetry is going to put me right here. Okay. But then I technically have to do negatives, but recognize that they really repeat, right? So I'm going to get this one, y-axis symmetry gives it over here again, and the x-axis symmetry gives me this one again. Okay, so that's kind of redundant. So then pi fourths, put that one in, get the plus and the minus, but that's going to be 0, and that doesn't actually do anything interesting. So what does this look like? Well, this looks about like this. It's a figure 8. And this figure is actually called a lemniscate. Lemniscate is Latin for ribbon, and so, or at least that's the etymology of the word. And so it looks like a ribbon, and that's why we get the name. Now to summarize, if you're trying to figure out what kind of shapes you have in polar equations, here they are. In general, if you have y is equal to tangent of some, if you have theta is equal to some number alpha, well, then you get a line passing through the pole making an angle of alpha with the polar axis. Well, if you have r cosine theta is equal to a, then you're going to have a vertical line equal to a. If you have r sine theta is equal to b, you're going to have a horizontal line at y equals b. If you have r is equal to some number that's positive, you're going to have a circle with radius a. If you have r is equal to plus or minus 2a cosine theta, you're going to end up having the situation where you have a circle shifted to the right or to the left with a radius of a. Then if you have r is equal to plus or minus 2a sine theta, that's going to be a circle shifted up or down with a radius of a. Then if you have r is equal to a plus or minus a cosine theta or sine theta, then you're going to get a cardioid. Now here, if b is less than a and you have a plus or minus b sine or cosine of theta, you're going to get a limacon without an inner loop. And then if you have r is equal to a plus or minus b cosine or sine theta where a is less than b, you're going to get a limacon with an inner loop. Then if you have r squared is equal to a squared cosine of 2 theta or sine 2 theta, you're going to get a lemniscate. And then if you have r is equal to a sine or cosine of 3 theta, you're going to get a rose with 3 petals. And if you have r is equal to a sine of 2 theta or a cosine of 2 theta, you're going to have a rose with 4